Hello everyone, today we're going to do an example question on Nernst equation. Okay, so first of all, let's read this question. The question is telling you to calculate the cell potential, okay, and then giving you the temperature at 25 degrees Celsius and give you a cell notation. So this way, this display is called cell notation. Okay, and then you're supposed to calculate the cell potential. Again, it's not standard cell potential, it's cell potential. So you realize, okay, I need to use my Nernst equation. Okay, and then let's write out this Nernst equation first. Okay, so Nernst equation is like this: cell potential equals to standard cell potential, which is that little circle, the cell knot. Okay, and minus RT and F ln Q. Okay, so this is applies to any temperature. Okay, and then if it's at 25 degrees Celsius, if it's at 25 degrees Celsius, and then we simplify the Nernst equation into this way. Okay, so it's cell equals to not cell minus. Okay, so basically we applied R is the constant. Okay, so we use 8.314, and temperature in this case is 25 degrees Celsius, but we'll turn it into Kelvin, and then over N will be the number of the moles. We need to keep that. That's coming from the specific the cell. Okay, and then F is current as constant, which is 96,485. Okay, and then so you plug all those numbers in, and then this equation turns into this expression. Okay, so it will be 0.0592 volts, okay, over N, again, number of moles of electrons involved in the half fractions, okay, and then now turns into log Q, okay. Q again is the quotient, okay. A log is a base of 10 and ln is log of E, so you have to be careful which equation, which format you're using. Again, the bottom format is at 25 degrees Celsius. Okay, so now with knowing that, again, apparently we can just use the equation on the bottom because it's simplified. Okay, and now let's see, what do we need to figure out the cell potential? Okay, so if you look at Nernst equation, so we don't know the standard cell potential. Okay, so we need to figure out that. Okay, and then also we need to figure out how many moles of electrons involved the half reactions, and then we need to figure out the Q. Okay, so Q seems easy because you have over here, if you read the question, the notation, you have those concentrations. Okay, so that will help you figure out the Q. Okay, so now the problem turns into how do you interpret this cell notation over here. Okay, so which we learned from the lecture. Okay, so now again, cell notation, we know the left side. Okay, so this two. Okay, this two over here. Okay, so is an anode. Okay, so it's an anode. This is your anode. Okay, oxidation half reaction happens, and this is your electrolyte. Okay, and then the double line, that's subbridge. Okay, so let's write that down. This is your subbridge. Okay, and then you have electrolyte again. Okay, so this is electrolyte. Okay, so it's electrolyte, and then you have your cathode. Okay, so that's the cell notation. Again, besides that, we know that at anode, what happens? Yeah, oxidation half reaction happens. Oxidation half reaction. Okay, and at cathode, the reduction half reaction happens. Then you go, why do I need this? This will help you to figure out E cell. Yes, okay, so the E cell, standard E cell, okay, equals to the standard, the reduction half reaction of this electrode potential, okay, minus an anode. Okay, one more time, we know that cathode is where the reduction half reaction happens, and anode is where the oxidation half reaction happens. Okay, so then these numbers, when you have this little circles over here, these numbers you can figure out these numbers, okay, from the table. Okay, so the table will be provided. Okay, so the table is called standard reduction potential, okay, at 25 degrees Celsius. Okay, so you can find those values from the table. Okay, and then now the problem will be what's the value for each one. Then that comes from writing out the reaction equation itself. One more time, we know at anode the oxidation half reactions happens, and then from oxidation half reaction we know that the oxidation number will increase. Okay, so that means over here you have tin, okay, as a solid. Okay, after the reaction, oxidation number increase turns into tin ion, okay, 2 plus. Okay, and then on the other hand, for the reaction happens at cathode, the reduction half reaction will be the oxidation number decrease. Okay, so then you have the silver turns back to silver ion turns back to silver. Okay, so this will be the reaction, and then of course we need to make sure this reaction itself is balanced. Okay, so one more time, let's write out the half fractions. This is the overall reaction, but the half fraction will be like this. So you have tin, this is your oxidation half. Okay, oxidation half. So you have tin turns into tin ion, and we know for oxidation half fraction the electrons are part of the products. Okay, so that's why we have loose electrons. Okay, and then reduction half reaction, so you have the oxidation number decrease, silver ion turns into silver. Okay, and then the electrons will be part of the reactants. Okay, so it's gonna be 1. Okay, so that's what we have. And then again, in order to make sure this reaction equation over here, this reaction equation over here is balanced, we need to cancel the electrons. Okay, so then therefore we need to multiply by 2. Okay, so the whole reaction equation multiplied by 2, then you add up. Okay, so then that means you also need to add the coefficients over here to make sure this reaction is the equation is balanced. Okay, so then from here we realize, okay, so we have 2 moles of electrons transferred throughout this redox reaction. Okay, so then the same time we'll figure out this n will equal to 2 in this reaction. Okay, and then now since we already know oxidation and reduction half, you go to the table we mentioned earlier, and this value will turns out to be, this will be 14. 14 is the negative 0.14. Okay, and for silver, okay, so this is gonna be 0.8. Okay, and then depends on the table you use, the numbers slightly different based off if you have more sig figs or less. Okay, so now we can use these values back into this relationship over here. Okay, so now you'll have excuse me, so you have E cell, not cell, or equals to the cathode reduction half, so that means you're going to use 0.80, okay, minus the negative 0.14, okay, so the oxidation half. So after you do this calculation, it turns out to be 0.94 volts, okay. So you have this value. Now we can put this into our Nernst equation, but before that we also need to calculate the Q. Okay, so the Q, you should look into this reaction equation itself. So that Q will equal to products over reactants to its coefficients. Okay, and then remember these solids are now going to be involved because they are now affecting the equilibrium. Okay, so then we're going to use the products to its the concentration. Okay, and then to its power is going to be 1, but silver, pay attention, it needs to be 2. It needs to be 2 because it has the coefficients 2. Now you can plug in the numbers. From the cell notation, we know the concentrations over here. Okay, so that'll be the tin will be 1.8. Okay, 1.8, and then over 0.055. Don't forget to square it. Okay, so you do this and you get a value. Okay, and then you take the log of it. Okay, so now you can just plug everything in. Okay, so now I'm gonna put everything into our Nernst equation. So E cell will equals to the standard inner cell, which is 0.94 volts, minus, okay, so that n equals to 2, we figure out from balancing the equation 0.0592 log, which is 10 based log of this Q. Okay, and then this Q, let's calculate real quick. Okay, so it's gonna be 1.8 divided 0.055. Okay, so it's gonna be 5. That Q is 595. Okay, you take a log of it, so this turns out 0.94 to 0.0592. This turns out to be 2.77. You finish off the whole calculation, this will be 0.86 volts. Okay, so this is how you use Nernst equation to calculate. Okay, so make sure you understand the whole process. Okay, thank you for watching.